Okay, let's get started. Last time we talked about this equation here. So this equation, which is Lagrange, Euler-Lagrange equation, which is equivalent to Newtonian method, right? Newtonian equation. So that's what we did last time. Again, this is for 1 degree of freedom. Last time we talked about 1 degree of freedom. Now, we're trying to generalize this case, but before I do that, I want to start with a single link manipulator. Okay, let's because this one is a different example. Now let me talk about a single link manipulator. Okay, so I'm not going to derive this equation. So since we kind of agree that this equation follows from Newton's second law, right? Okay, this is the Newton's second law, and that equation, Lagrange equation, follows from Newton's second law. So we kind of agreed on that, and this is true for any degree of freedom. Okay, so we can prove that in general, but you know, it might take 2 full classes to prove that. Okay, so that's why I'm not going to do that, and that's not too important for the robotics, right? So mainly you will have to use the formula. So that's why. Let me take you to the other example here. So here you have the single link manipulator. As you can see here, this guy is so this is the motor here. This thing is motor, and there is a shaft connecting the motor to and this object. So this is actually this is the link of the robot. Okay, this is the link of the robot, and the length of this robotic link is L. Okay, this has a length of length L. Okay. Now this is the revolute joint, because we have, you know, since we have motor, right, meaning definitely the joint is revolute. Okay, motor is going to rotate this link. Now the thing is, what is the angular displacement for the link? For the link, angular displacement is theta L. For the motor or shaft, they are both connected, right? So even though I call it theta M here, so this includes shaft also. Okay, motor plus shaft. Motor plus shaft is theta M because they are single system. So angular displacement of this single system is theta M, and angular displacement of this link of the robot is theta L. Okay. So how are they connected? The difference, the ratio of these two, theta M and theta L, is called gear ratio. So we have heard of gear, right? In engineering, gear, right? We have heard of that, gear. So gear ratio is the ratio of theta M and theta L. By the way, this is theta L, okay? This is theta L, this is theta M. So this is theta L and this is theta M. And the ratio is called R. And since this is ratio of angle and angle, right? So theta and theta. So that's why this ratio does not have any unit. So gear ratio is unitless. Okay. Now our goal here is to find the kinetic energy and potential energy of this robot. Okay. So yeah, I don't think I have to. I think you will understand here, right? So here, Jm, again the inertia. So what is the kinetic energy of the rotating object? So kinetic energy K of rotation. Kinetic energy of rotation is similar to translation. 1/2. So mv square, right? What is the corresponding part quantity in rotational motion for m. I, moment of inertia. M is I, V square is omega square, right? So that's the kinetic energy in the rotation. So that's what I'm going to use here. So I call it J here, okay? I is J. So we have the two kinetic energies here. One kinetic energy of rotation of the motor and shaft, which is a combined system, and the kinetic energy of the link. Okay, this is the link. So what is the kinetic energy of shaft and motor? 1/2 Jm, my I is Jm here, where Jm is the inertia of motor and shaft both. Okay, so Jm is inertia of motor and shaft. So that's inertia, 1/2 I. Then what is the angular velocity of the motor and shaft? Theta m dot squared. That's the velocity square, right? Or angular velocity square, which is omega. Okay, so this part is done. This part is done. Now let's talk about the kinetic energy of the link now. How do you find the kinetic energy of the link? Again, 1/2 I omega squared is the same formula. Then I is, in the case of link, I call JL. JL is the inertia of the link. So 1/2 JL omega square, which is for the link, we have theta L, right? So theta L dot square. Okay, so far so good here.
What was J again?
Oh, J is, for the inertia, I call it J in this. We used to call it I, right? Inertia.
Okay.
Yeah, I simply call it J here because I want it to be consistent with the book. That's the idea, You can simply call I also, but I want it to be consistent with the book. Makes sense?
Yeah, it makes sense. It just feels
Jacobian, right?
it just feels like unnecessary. Or that's exactly what I thought. Like it was Jacobian.
Yeah. Yeah. At some point, I thought, okay, should I change the notation? And I realized, okay, because the book is using J, so I want to be consistent.
Okay.
Okay.
Thank you.
Yeah, I was also confused, like, what? Jacobian? Yeah. Yeah, but I want to be consistent. Yeah, that's a good catch. Yeah, so now I factor out theta I dot square in both the terms. As you can, I replace this theta m by r theta L, because you have to take the derivative of theta m, right? When you take the derivative of theta m, then what do you get? R is ratio, which is constant. Then you simply take the derivative of theta L, right? So theta m dot is r times theta L dot. So if you square theta m dot square, then you get r squared theta L dot square. That's what we have here. So r square theta L dot square, because I already factored this out, right? From this term and from this term. So then r square Jm plus JL is JL, then we have 1/2 factor out and theta L dot square. So far so good.
Think so. Yeah.
Okay. Then finally, I'll call this guy simply J, okay? I'll simply call this J. Okay, 1/2 J theta L dot square. I'll call this J finally. Now, before that, let's go do the potential energy. What is the potential energy of the system? So let's talk about the potential energy of this guy. Okay, so what is the potential energy of this motor and shaft? This is not moving, right? This is just lying on the floor. Only thing that moves is this guy here. This rotates like this. Okay, let me take you to the, let me stop this sharing and let me take you to the other, here. What I meant is this. Oops. What I meant is, because this is the guy, we have a motor and shaft. And the thing is, I cannot do the nice picture. That's the problem. So this guy, this is motor and shaft, and the other one, I don't know. The link moves like this. This is motor and shaft, right? And link is attached here in the beginning like this. Then this link will move like this. Oops. This will move like this. This will move like this. In this is how it rotates, right? See, this link rotate like this. Okay. So in that case, what can I do here is, so let me consider my link like this. So this is my link in the beginning. So what is the angle for the link? Theta L. This is the theta L for the link. Okay. Then, so how do we find potential energy of this guy is 0, right? Because this is on the ground, right? So basically this is on the ground. But only this guy rotates. This guy only rotates. So suppose this is the ground, and while this guy rotates, my position at some point of time is here. This is this link, okay? This guy is this link. Okay, right here. This is the link like this. So when this guy rotates, so the angle of rotation of the link is theta L, right? So what is the height of the link above the ground? This is my height at particular time. This is the height of the link above the ground. Then what is this h? We have to figure out the h. Then our potential energy is mgh. So what is h? So what is the distance from here to here? So this is the center of mass, right? When you talk about the distance of something from some point, then you take the center of mass, right? So this distance, actually this whole thing is L. Actually, this whole thing. Okay, this is my L. This is the link, right? And what is the center of mass of this link? L over 2. Okay, and this angle is theta L, right? This is theta L. Then what is my h? H equals L over 2. Okay, h equals, let me make it clearly here. H equals the whole thing minus this thing, right? This h equals this is L over 2 minus this x. H equals L over 2 minus x. And this is theta L, right? This is theta L. What is x? This is also L over 2, right?
Would it be x would be equal to L over 2 cosine theta?
Exactly.
Oh, cool.
So then you just plug in here, L over 2 factor out, then 1 minus cosine theta L. That's my h. Then multiply by m and g. That's your potential energy.
My bad. Why is it 1 minus cosine L? Or cosine theta L?
Because my h is L over 2 minus x, right?
Right.
But my x is L over 2 cosine theta L. So I just plug in here. I plug this in here. L over 2 cosine theta L is there. Now I factor out L over 2.
Okay.
Make sense?
I think I'd have to look at it for a little while. I'm sorry, I'm not sure what I'm not getting about it.
So do you know what the x is, right?
Right, x is equal to L over 2 times cosine theta L.
Then what is your h? H is L over 2 minus x.
Right.
So h is L over 2 minus x. So you have L over 2 minus L over 2 cosine theta L. Then you have factor out L over 2. You get 1 minus cosine.
Oh, okay, now I'm getting it. My bad. Yeah, that
That's
makes
fine.
complete sense. Thank you.
So that's what my H is. Now mgh is our potential energy. Let me share the screen again, okay? Now you can see it now, right? So that's why my potential energy is mg L over 2 1 minus cosine theta L. Okay, now what is my Lagrangian now? We have to make the Lagrangian now, right? So let's make the Lagrangian and solve the problem. That's all. Okay, what is the Lagrangian now? Make Lagrangian. L is k minus p. So k is, so we have 1 over 2 r squared jm minus jl theta L dot squared. That's my k, if you remember from previous. Then my p is mg L over 2 1 minus cosine theta L. So what is my equation? What is my Lagrange equation? du over dt, then partial of Lagrangian with respect to, what is my generalized coordinate here? Help me. What is my generalized coordinate in this Lagrangian?
Theta?
Theta L, right? It's because we have two theta, one is theta M, the other one is theta L. So theta L is my generalized coordinate. That's why I'll rewrite this as theta L dot. Okay? Minus dl partial of L, we say to theta L now, not dot, equals tau. That's my Lagrangian equation. So what do you get here? So what is the first term? You get, let me rewrite this Lagrangian. My Lagrangian is 1 over 2j theta L dot square minus mg L over 2 1 minus cosine theta L. That's my Lagrangian. So what is your delta partial of Lagrangian with respect to theta L dot? So 1 over 2j, what is the partial of theta L dot squared? 2 theta L dot, right? That's the partial. Now you have to take the derivative of this guy again with respect to t, because we need that here. So what do you get here if you do that? If you do that, you do again the further derivative of this guy with respect to time. Then what do you get? These 2 and 2 cancel anyway. So j now with respect to time now. Then you get j theta L double dot. Right, question? So far so good, right? Now let's do this part here, this part, then we'll subtract. So what is delta partial of Lagrangian with respect to theta L? What is the partial of this thing? So you have the Lagrangian here. This is my Lagrangian. So this term has theta L dot, right? So the partial of L with respect to theta L is 0. From this term, we get 0. Then we have minus mgl over 2. Then what is the derivative of 1 with respect to theta L? 0. Minus, what is the derivative of cosine theta L? So minus sign, right? Minus. So minus minus plus, minus minus. Minus minus plus, plus minus minus. So mgl over 2 sine theta L. Then what is your Lagrangian? Your Lagrangian is two terms together, right? So this guy is j theta L double dot, and minus you have minus here. This is from the formula, this is from the derivative. So you have minus minus mgl divided by 2 sine theta L equals tau. So which is j theta L double dot plus mgl divided by 2 sine theta L equals tau. Guys, question here. So I'll stay here until I get the green light. This is important. Please.
Sorry, that's probably so loud. Try not to talk because someone's doing yard work, but
That's okay.
I think so. I think I'm okay. Personally.
Any other question, guys? Because this is our first problem in Lagrangian, right? So that's why I want to make sure everybody gets it. So let's move ahead then, okay? So now this t, t could be, well, I'll leave it here. Okay, the t could be, once you do this, then you are basically done. But if you want to go a little further, I'll give you that TL is mainly two terms here, U and damping component. Oops. So I just give it to you, okay? You don't have to, but so this is my TL. So tau L is can be found that tau L is U minus BM theta M dot minus BL theta L dot. What is U? U is the input motor torque. Okay, you have the torque from the motor, right? So that's the U. And this BM and BL, they are the damping component. So that's why I put minus and minus here. Okay. Then I can rewrite this guy as U minus. So if I use the same thing again, theta m dot equals R dot theta L dot, then I can simply get RBM plus BL here, theta L dot. Okay. Then this is my right hand side, and I can rewrite this equation as theta L double dot plus this guy. If I take it to the left hand side, then become plus, I can simply call it B here, plus B theta L dot plus MGL over 2, then L over 2, then sine theta L equals this U here on the right. Okay, so this is not too much important. These steps are not too much important. As long as you guys understand this, you should be okay. Okay, right. That being said, let's go to the next slide. Okay. Now we verified that this is important for our robot, right? We solved one problem, which is single link manipulator, right? So we solved one problem. Now we realize that this is important for us. Now let's try to generalize this for the N link. Now from single link to N link robot. Okay, that's what I'm taking you guys. From single link robot to N link robot now. So this is what we did. Now let's do the N link. Now to do the N link, okay, let's make the background for the, if you want to go to the N link robot, I need some background concept, okay? So what I need is, now our goal is to define the kinetic energy for, because I need the Lagrangian, that's the whole idea, right? So I need the kinetic energy for the N link robot, and also I need the potential energy for the N link robot. So let me begin with potential kinetic energy for the N link robot or manipulator, right? Then after I'm done with this kinetic energy, then I'll be talking about potential energy for the N link robot. Then I'll subtract potential energy from kinetic energy, and I call it Lagrangian, right? Then once I have the Lagrangian, then I can plug in the formula, Lagrangian, Euler-Lagrangian equation, then we can find the equation of motion. That's the whole idea. Okay. So now I want to emphasize here that DH joint variables, you know what DH, right? Dynamit-Hartenberg joint variables are the generalized coordinates. Okay, so we already know about the DH convention. So in the DH convention, whatever we have in the as joint variables, those joint variables are generalized coordinates. Okay. Now kinetic energy is 1 over 2 mv squared, right? So basically, if you want to do the kinetic energy, it's 1 over 2 m v squared. So how do you write b square in the vector form? So b transpose and b. That's how you write, right? B square. In matrix form, this is how you write. Because b square is b dot b, right? You know this, right? B dot b. So b dot b is ax square, bx square plus by square plus bz square from here. Then to get this from the matrix multiplication, you have to do this. Vt and Vt, Vt and V. Okay, that will be my kinetic energy term. Again, kinetic energy, we have two terms for kinetic energy. This is one of the terms, which is the translation part, right? Then obviously, what is the rotational part? 1 over 2 inertia times omega square, right? Inertia times omega square. Moment of inertia times omega square. So this is what we, for the symmetric object, point object, this is the formula we used to use for the kinetic energy of the rotation. But in our case, so we might get any object, right? Not only in a regular object, it could be any general object. So that's why, so we write this. So we have these two terms, but we write this little differently. This guy will be little different, as you can see in the next slide here. So this is my rotational term. As you can see, the translation term is whatever we saw in the previous slide. Okay, translation is this guy here. So 1/2 m BTV squared, BTV. But the rotation term, so instead of simply 1/2 I omega square, instead of simply having I omega square, we are having omega t I omega. Because this formula is for particular object, okay? It's a symmetric object, that kind of object for the symmetric object, and having x, y, z, all momentum inertia, equal to each other, and that kind of very nice symmetric object. So this formula is true. But for any object, this is the formula for rotational kinetic energy, which is omega transpose I, okay, and omega. Okay, so this is for the arbitrary rigid body. Okay, any rigid body. That's what I meant. So I'm not going to derive this guy, but if you want, you have the full derivation here. Okay, if you once you have time at home, you can go through it. So this is how you get this one. Okay, so we get this kind of term there instead of getting a nice I omega square, 1/2 I omega square, we get 1/2 omega t I omega. Okay, so you can, this is not so much. Yeah, go ahead.
Oh, sorry, just a quick question.
Yeah, absolutely.
The I there, what's the little squiggle on top of it mean?
Yeah, they want to make it different from normal I, right? That's because.
Oh, okay.
Yeah.
So it's just distinguishing it from others. Okay, cool. Thank you.
Yeah, so they want to make this different, this guy different from this guy. Okay, they put this squiggle sign there.
That makes sense.
It depends on the book, or resource, online resources. This is from, yeah, in the PowerPoint I have put, I have the link to this page. Okay, where I got this page from. Okay, but yeah. So this is again, let me summarize. So again, this guy is translation kinetic energy, and this is the rotational part of the kinetic energy for arbitrary rigid body. So here, V is the linear velocity of the center of mass. So you know what center of mass is, right? So for example, if you have something, you have this object, right? Find a point where you can balance this guy. See, I balance this guy, and that point is center of mass. Okay, so V is linear velocity of the center of mass, and omega is the angular velocity about center of mass, and I is obviously inertia tensor. Now we call it inertia tensor. So this is not, this I is not this I. So this is the simple inertia, moment of inertia we call it. But when you write this in this form, we call it inertia tensor here, okay? And that inertia tensor is expressed in inertial base frame. Again, we have two frames here. If you see, this is the base frame. And there is another frame here, which is right at the center of mass of this rigid body. See this oval? This is the oval rigid body here. So on the center, in the center of this rigid body, we have a frame. which is called body attached frame. So when I say I is the inertia tensor, I have the inertia tensor expressed in the inertial or base frame, not in this frame. In this frame, okay, not this frame, rather this one. So I is expressed in base frame. That's what my I is. Okay. All right, how do I find that I? That's the thing now. So how do I find this I? Okay, to find this I, so it will be clear once we do one problem. So, but for now, let me go over this slide and then do a problem, okay? So we know this relation here, right? So we know R dot equals S RT. So this is from previous chapter. So if you multiply this guy by, so how do you get this relation from there? Help me. How do you get this guy from this guy? Take the transfers from the right hand side. RT, multiply by RT from right here and also here, right? Multiply by RT on left and right hand side of the equation. Then you get, this is 1, right? RRT is 1. Then you get S omega equals R dot RT. Okay, so what I'm trying to say is, once you have R and RT, then you can find omega. Because this skew symmetric matrix has the argument omega. So this matrix has the term which is omega. And you can equate that matrix with that matrix, which is the product of these two matrices. If you equate left hand side and right hand side, then you can form some equations and figure out omega by comparing left hand side and right hand side. Okay. Now, when I say inertia, there could be two kinds of inertia again. One, the inertia related to the body frame, and the other one, inertia with respect to the base frame or inertial frame. Base frame is also called inertial frame. So inertia, you can have two kinds of inertia. One related to the body frame, the other one related to the base frame. How do you convert one inertia to the other inertia? Okay, so if you are given the inertia in the body frame, how do you convert that inertia to the base frame? That's what I'm asking. So does something click in your mind? We did something similar to that in previous, in chapter 1. So if you are given a quantity in one frame, how do you convert that quantity in other frame? What kind of transformation we call it? Similarity transformation. Okay, if I show you the slide here, see that? This is what we did in the first chapter, right? Okay, so if you want, so what I meant is, if you are given the inertia in body frame, this is what this guy is. This guy is body frame. Then you can convert this body frame inertia to inertia in the base frame or inertial frame. So inertia in the base frame is this I, and inertia in the body frame is this I here. Those two I are different. This is I don't know, what do I call? This is I, this is big I don't know. Okay, so this is how they are related. And this transformation is called similarity transformation, right? Now I want to mention some property of those two I, this I and this I. So this is the body frame, this I. let's talk about this I here first. So this I is the inertia with respect to base frame. That's what that I is. And that I is dependent upon the configuration. Okay. But the inertia in the body attached frame is independent of the configuration. That's the two main differences between these two I. This I depends on, so this I here, this. Did I say the other way around? So this I depends on the configuration. This I is independent of the configuration. Okay. Now what is that I now? What is inertia matrix, right? This guy is 3 by 3 matrix, right? This guy is 3 by 3 matrix. Inertia. Let me write that guy in the matrix form. That's what my inertia matrix looks like. That inertia matrix looks like this. So I equals IXX, IXY, IXG, IYX, IYY, IYZ, IGX, IGY, IGZ. Okay. Remember, you have the diagonal elements here. This is diagonal. Diagonal elements are called principal moments of inertia. They have a special name given to it. So these diagonal elements are called principal moments of inertia. Okay. And off diagonals are called product of inertia. Okay. Off diagonals are called product of inertia. So principal moment of inertia and product of inertia. There are two different names for these components. This is principal, diagonal principal, and these are product of inertia. All right, so now before I go to the next slide, let me define what is I. What do I mean by this? So this I could be XX, II meaning XX, YY, GG. That's how they are defined. This, I'm trying to define this component here, diagonal component. So whether this is XX or YY or GG, you define this way. So volume integration, again, this is calculus 3. So volume integration, you have 3 integrals. Then R squared dm. Okay, it's very easy to understand here. See, what is the inertia? How do you define the moment of inertia in physics 112, 111? Moment of inertia is 1/2. Oh no, not 1/2. M summation M R squared, right? That's how you define the moment of inertia in physics 111. Summation M R squared. So in our case, we have simply summation replaced by integration. Okay, M replaced by dm. Then R squared is R squared. See that? This is just the counterpart of this guy. I is defined as summation M R squared, which is integration of R squared dm. Okay, again, this is volume integration. We have 3 integral here. Then R squared. Now how do you rewrite dm? Because rho equals m over v. So then what is your m? M is rho v, right? So that's why rho times v, dv. Okay, again, dv is dx, dy, dz. So if you want to find Ixx, or then you use this formula. Okay, now let me summarize this. So okay, so Ixx, this is the formula. As you kind of saw that in the previous here. Now, depending on which plane we are talking about, your R will be different, right? Depending on which plane you are talking about. In the XY plane, this R will be x square plus y square. Okay, so that's what I meant. In the XY plane, you'll get IGZ. Okay, so which is x square plus y square rho dx dy gg. Similarly, IYY is this x square plus z square. Then IXX is this one here. So these all three are called principal moment of inertia. And the other 6 so are defined by this. By the way, the other 6 there, so IXY equals IYX, IXZ equals IZX. That's how they related. Then IYZ equals IGY. So other 6 terms, now we are basically doing the 3 terms now. In total, we had 9. So 3 here and 6 here. Out of 6, now since they are related, we just can calculate 3, and other are exactly the same. XY equals YX, and so on and so forth. And this is the formula for finding those product of inertia. So what happens if the object is symmetric with respect to body attached frame? If the object you are talking about, let's say you are trying to find the moment of inertia of certain robot, right? If that robot is symmetric with respect to body attached frame. Remember, we have 2 frames, one the body attached and the other one base frame. So if it is symmetric to the body attached frame, then all those guys, all these are 0. All of them will be 0. Okay, this will be 0. That's the good news. So you are end up just calculating just these 3 now. But first of all, you have to make sure it is symmetric. Okay, otherwise that doesn't happen. Okay, make sure your body is symmetric. So let's do one problem, guys. Do you have 5 minutes? If you have, just I can finish this problem.
I gotta be somewhere at 3, but if you keep it in 5 minutes, that's fine.
Well, then I didn't hurry. Okay, then I'll do it next time then. So I thought this will be interesting because we have done a lot of theoretical things. So, all right, I'll do this next time then.
Sure thing.
All right, then.
So if any question, otherwise I'm done.
I don't think so.
Okay, good.
Okay. Take care, everybody.
All right, stay safe, guys.
Thank
You
you.
So could you put the slides on Moodle?
I can do that.
Okay.
All right.
All right, sir. Thank you. See you
Also,
tomorrow.
I have the
Yes, sir.
I have the video also, right? Have you noticed that?
Yeah, the video.
Oh yeah,
Oh,
I upload the video also.
Okay, perfect. Yeah. Thank you, sir.
Yeah.
Take care.
All right.